All right, let's get started, everyone. So for the second half of the day, we have Virginia Williams, our very own from here at MIT. She's done a bunch of interesting work in many topics, but one of the things she's most well known for is being the pioneer of fine-grained complexity. All of you who studied NP completeness and other notions of hardness from the beginning probably wondered, okay, but this is polynomial versus not polynomial. And it turns out that one can actually reason about sort of fine-grained complexity. Is it possible to do something in time n cubed or n squared and so forth? And many of these ideas originated with Virginia. So we're very lucky to have her give us a tutorial on these topics. So take it away.
Thanks for the very nice introduction, Guy. So hi, everyone. If you can't hear me, let me know. I'm going to try to speak up. As Guy said, I'm going to tell you about fine-grained complexity. So let's begin. What is the central goal of algorithms research? We want to know how fast can we solve certain fundamental problems, right? How fast do we want to solve them? Well, as fast as possible, but usually you have to read the input. So let's say I give you some function you want and some input. You want to evaluate the function on the input. The input has length n. And typically, you have to read it, so the best you can hope for is a linear time algorithm. And that's what we really, really want. And so the good news is you've taken a lot of algorithms courses, and we have a lot of techniques. You can throw all these techniques, and you can solve a lot of problems in linear time. There's a list of techniques over here. Now, unfortunately, I want to say that all the problems we care about, they do have some algorithms, so they are solvable. So problems in NP and EXP and so on, they have some certain search space, and you could always brute force, do an exhaustive search over this search space. So there's always some way to solve the problems. And even in 1956, Gödel asked, basically, how can we do better than exhaustive search? When can we do better? And it turns out that for many fundamental problems, we can't even do better than exhaustive search. It's kind of ridiculous. Even though we have all these techniques, we don't know how to beat the simplest algorithm out there. And so what do we mean? So I'm going to talk about hard problems. What are hard problems? They come from all over the place. They do have some simple algorithms. Often it's an exhaustive search algorithm, or often you just throw some techniques at it. You throw dynamic programming, you throw greedy algorithms, whatever you want, and you come up with some algorithm. And you can analyze it, and unfortunately you get some horrible runtime like 2 to the n or n to the 10 or something like this, and you're not happy because you're not close to linear. They're very slow. And you look in the literature, and you see no one has done better. Even though you came up with a very, very simple algorithm, no one got anything much better than that. And it can give you a bit of a headache, and you wonder why. So here's the canonical example. You've all seen the satisfiability problem. So you have a Boolean formula over n variables, x1 up to xn. The formula has a special form. It's a bunch of clauses ANDed together, m of them. Every clause is of the form y1 or y2 or yk, where yi is either a variable or its negation. For example, this thing over here is a 3-sat formula because in every clause you have at most 3 literals. And your job is to figure out, is there some Boolean assignment to the variable so that you satisfy all the clauses? Of course, there is an exhaustive search algorithm. This is a problem in NP. You can just brute force over all possible Boolean assignments of the variables and plug them in, and you basically get a 2 to the n times the length of the formula algorithm. What is the best algorithm for this problem? Well, it is basically 2 to the n minus some constant, think of it as 1, times n over k. K is the number of literals in a clause, times the polynomial, the length of the formula. And unfortunately, however, as k, the length of the clauses grows, this goes to 2 to the n, which you could have just done by doing brute force. And these are somewhat complicated algorithms, yet for formulas with very large clauses, they don't do much better than exhaustive search. And we don't have a 2 to the n to the 1 minus epsilon time algorithm for any epsilon bigger than 0. There's no 1.99999 to the n algorithm for this problem. Okay? And that's why we think of it as hard. You can't really even beat brute force. Here's another hard problem. Okay, this is, to you it may seem simple. So I give you two sequences of letters. Let's say ACTG, and both of the sequences are of length roughly n. What do I want? I want a subsequence, so like a sequence that appears in both of these sequences. Let's say this blue one over here, that is of maximum length. You can think of it as an alignment problem. You put every letter of one sequence on top of a letter or a gap of the other one, and you try to align them. So this is a measure of similarity. You want to know how similar to DNA sequences, for example, are. You can solve this problem in quadratic time. There is a very simple dynamic programming algorithm you can run. We teach it in our algorithms courses. It's quadratic time. The best known algorithm is n squared over log n squared from the 1980s. And there's nothing like n to the 1.99999. Okay, you can shave a little bit, but you cannot get something like this for whatever reason with the current techniques. And while this is a polynomial time solvable problem, I still think of it as a hard problem because you can solve it very easily in some time, here n squared, but once you get there, you can't seem to beat it. Okay? On the face of it, this problem has nothing to do with the previous one, right? One is in n squared, the other one is in 2 to the n. But you know what? They're very similar. And in fact, with fine-grained complexity tools, you can actually relate them to one another. All right. So to recap, we have a bunch of these problems where our current techniques get stuck. You can get some simple algorithm and analyze it and get t of n time, which is much slower than linear. But we can't do better than t of n in the exponent. You can't get t of n to the 1 minus epsilon. For SAT, t of n was 2 to the n. For longest common subsequence, it was n squared. All right, and people have studied these problems forever and ever. We still study them, and we're still stuck. Why are we stuck? And more importantly, are we stuck for the same reason? Could we just show that these are secretly the same problem? And if they're the same problem, we just find out one technique that solves them all, and we're done, right? That's what we want. Okay, so this is the question, or two questions we want to address. So what I'm going to do for the rest of this tutorial lecture is first I'm going to talk briefly about some traditional hardness attempts in complexity theory and why they don't really answer our questions. Then we're going to, I'm going to show you what the fine-grained approach is, and then I'll give you a hardness example, okay? And in the second tutorial lecture, I'm going to give you many more examples. So this you can think of as just an introduction, and it's somewhat more lightweight, so hopefully all of you will follow it. And then the second one will go really in depth. Okay. So let's talk about hardness and complexity. So here's a theorem that one can prove in complexity. You can prove that for any natural computational model, like a random access machine, pointer machine, Turing machine, whatever you want, you can show that for every C, there are problems that you can solve in n to the c time with some algorithm, but you cannot solve much faster than that, n to the c minus epsilon. In fact, even better theorems are known. You can show that there are problems in t of n time, which you cannot solve faster than t of n time, even by polylogs. So you can prove this. Unfortunately, there exist problems. Okay, these problems are very specialized, very hard, and complicated, whereas what we care about are particular problems, like SAT and longest common subsequence. So if we can show the same sort of theorem for our favorite problems, we would be done, but we don't know how. So computational complexity can only show that there are problems with of this nature, but not that the particular problems we care about have this property. And in fact, if you look at SAT, for which the best algorithm is 2 to the n, complexity can't even show that it doesn't even have a linear time algorithm. So in fact, it could be solvable in linear time. We just don't know how. Well, no one believes it, but okay. So what else do we know? Well, we know about P versus NP, okay? So P are all these problems, decision problems, meaning that their answers are yes or no, that can be solved by some polynomial time algorithm, an algorithm with a running time n to the 10, n to the 100, for n being the size of the input. And NP are the same sort of problems, except instead of having an algorithm that solves them, they have an algorithm that can verify their solutions. If someone gives you a solution, you can check, yes, that this problem has a yes answer, okay? It's known that P is in NP, and the famous P versus NP question is P actually equal to an NP? And people don't believe this. So everybody thinks that P is not equal to NP. What does this have to do with everything that we've been talking about? Well, there's this Cook-Levin theorem, Cook-Levin-Karp. Basically, it says that K-SAT, the SAT problem, is actually NP hard for every K at least 3. So this just means that if we had a super fast algorithm, like a linear time algorithm or a quadratic time algorithm for SAT, then P would be equal to NP, something that no one believes. And because of this result, we can say that SAT is hard, but it's kind of hard in the sense that it probably doesn't have a polynomial time algorithm. It doesn't say that it doesn't have a 1.9 to the n algorithm, beating a 2 to the n time. It just says there's no polynomial time algorithm. But at least it's some sort of hardness. And this is a conditional hardness. It's only hard if you believe P is not equal to NP. Okay? So, just a very quick recap for everybody. Okay, what is NP hardness? We make an assumption, P is not equal to NP. Then we show that if some problem Q has a polynomial time algorithm, then you can solve every problem in NP using this algorithm, also in polynomial time. And because we assume that P is not equal to NP, we conclude that Q requires superpolynomial time. Okay, so this is just how NP hardness reductions go. You make this assumption, P is not equal to NP, then you assume that some problem can be solved in polynomial time, and that if you can use this algorithm to solve everything else, then you get a contradiction, and therefore Q is hard. Okay, so what we want to do is get some sort of hardness for our problems that already have polynomial time algorithms. So what I want to say here is that if you look at the structure of this hardness proof, you can see that no problem that can already be solved in polynomial time can be NP hard, right? Because then this part here will be true. Q already has a polynomial time algorithm, so this assumption, so basically if P is not equal to NP, the second part can't be true. So you cannot use NP hardness to show any sort of hardness for a problem that already has a polynomial time algorithm. Okay? So we cannot, like for the longest common subsequence where we were talking about quadratic time, you cannot use NP hardness. And we actually want problems in quadratic time to be hard. All right, and the real problem is that NP hardness is too coarse-grained. It only talks about polynomial versus not polynomial. And we actually care about quadratic. All right, so let me take a little step back and talk about why people care about NP hardness and why they thought that polynomial time is efficient. Okay, the reason why is not because we think n to the 100 is efficient or that n squared is efficient. It is because it allows complexity theorists to kind of wave away any assumptions about the computational model. Because whether you use a Turing machine or a RAM or whatever, all these computational models can be basically translated from one to another with a polynomial overhead. So if polynomial time is thought to be efficient in one model, it's also efficient in another model. Also, if you compose two efficient algorithms, and efficient means polynomial, you take one algorithm and use it as a procedure inside another one. If the procedure runs in polynomial time and the overall algorithm also runs in polynomial time calling this procedure, then the full thing is has running time polynomial of a polynomial, which is still polynomial. So these are two main reasons, and it is not because of this. So what we're going to do is we're going to actually forget about polynomial being efficient. To do that, we're going to actually fix the model of computation. Pick your favorite model of computation, like a random access machine, and now we don't actually need polynomial to mean efficient. We can actually pick your favorite running time, like linear, and that would be efficient. All right. So what I'm going to show you now is how how you can mimic NP hardness and show hardness for problems that also can have polynomial running times, or just hardness that is actually based on the running time itself. Okay, so I'm done with this. Do you have any questions about the first part? Yeah.
Is there any hope that the time hierarchy theorem, right, can be replicated in more kind of explicit terms, right? I mean, like maybe come up with an explicit collection of problems, at least one of which should run into the C time. So.
That's interesting. So the main issue with using things like the techniques behind the time hierarchy theorem is that a lot of the problems we care about are very structured. Like, for example, they can be solved in like low space or something like this. Like, they're very, very structured. And
so I guess one thing I thought about is, right, both SAT and LCS, they have good non-deterministic algorithms.
They do. That's the other issue.
Right, that's the issue.
So that's another big issue. So there's too structured, and so this sort of hardness is too constrained. So.
Right, so conversely, are there any natural problems where, which don't have this kind of structure, like even non-deterministic algorithms would take a long time or something? Right?
Probably. Yeah. I mean, yes, I think so. But even then, I don't know how to do anything.
Okay.
All right, thanks. We can think about it offline, too. Other questions? Yeah.
So I guess I didn't totally follow one slide. So there's no hope that you can't use NP hardness to show that LCS, show directly something about LCS, but is there some hope that you could base the n-squared hardness of LCS on saying, okay, if LCS runs in n to the 1.99 times, then I can find some NP hard problem that runs in polynomial time?
That would be great, except like you need a very weird reduction that's like self-improving or something like this. Because like the current notion of hardness is that you allow any sort of polynomial blow-up. You need to restrict the polynomial blow-ups you allow, or you need to have some sort of theorem that says if you can get this running time, you can actually get an even better one. There's some self-improving sort of thing, which we don't know how to do. All right. Okay. All right. Yeah.
How much of these are model dependent?
So basically, once you fix your model, you have to. I'll get into this, okay? But basically, we're going to define some notions of reductions, and these reductions they're algorithms, and they have to be inside your model. So in that sense, they will be model dependent.
I've seen some weird things with like communication complexity to bound like the Turing machine head has to go by so many times, whatever.
Yeah.
I'm just asking, like morally, like how much does that apply to any reasonable computational model, that kind of stuff?
I mean, this sort of thing will apply to any model. It's just that how you count the number of steps will depend on your model, right? So yeah, with the Turing machines, you have to be very, very careful, and especially if you have multi-tapes and so on. But you'll see, like, it's very general. Okay, let me get to it. Okay. All right. So I'm going to tell you what the fine-grained approach is, and the way I'm going to do it, I'm going to contrast it with NP hardness. Okay. All right. All right. So here's like a very crude way to think about what NP hardness is. You assume P is not equal to NP. Now we know that SAT is NP complete. So this assumption is exactly the same as the assumption that SAT requires super polynomial time. So these two are the same. So you make the assumption that SAT requires super polynomial time. Then you take your favorite problem Q, okay, whatever Q is. Then you show that if Q has a polynomial time algorithm, then you can use that polynomial time algorithm to solve SAT in polynomial time. Okay? That's usually done with a reduction. And then from these two, you conclude that Q must also require super polynomial time. Okay? Now, what we're going to do is like this. We're going to change our hardness hypothesis. We're going to take some hard problem, H. It could be SAT. It could be something else. But instead of assuming that it requires super polynomial time, we'll assume it requires H of n time. So H of n is some function in terms of the running time. It's 1 minus little o of 1. This means you can save some sub-polynomial factors in the running time, but essentially you won't be able to get H of n to the 0.999. You make this assumption, you fix your machine model, for example, RAM, or you can take a Turing machine, whatever. You fix something here. Then you do something. This is a consequence of something that I will show you in a little bit called a fine-grained reduction. You will show that if you take your favorite problem Q, and if somehow this problem Q has a RAM algorithm that runs in Q of n to the 1 minus epsilon time, then this would also imply an H of n to the 1 minus delta time for your hard problem. So in other words, if you get much better than Q of n for Q in the RAM model, then you would also get much better than H of n for H in the RAM model, which would contradict this assumption. And therefore, it must be that Q requires Q of n time on a RAM. Okay, so basically H and Q can be different running times. And the problem is, how do you relate these running times for the two problems, Q and H, which is what I will show you. So we'll go through it one by one. The first thing I will show you is what kind of hardness hypothesis you can make. Then I will show you what these reductions are, and I'll contrast them. And then we'll see some results. Okay, let's start with the assumptions. So we know that SAT is NP hard, but besides NP hardness, there is something called the strong exponential time hypothesis, called SETH for short. And it says the K-SAT on n variables and m clauses cannot be solved faster than 2 to the n time. Poly-m is a polynomial in the size of the formula, and the point is that you cannot beat brute force for every k. Okay? This is what it means. So it's really, if I read it to you, it says for every epsilon for which you supposedly can solve SAT faster than 2 to the n time, there is some clause with k, so the k-SAT cannot be solved in this much time. So no matter what improvement over 2 to the n you claim you have, I will point to a k so that your algorithm cannot solve SAT on k-SAT formulas. All right? This is the strong exponential time hypothesis. And we can use this instead of p not equal np as our starting point. Notably, this is much, much stronger than p not equal np. P not equal np says SAT doesn't have a polynomial time algorithm. Here we say SAT doesn't have better than 2 to the n running times. Okay, between polynomial and 2 to the n, there's a huge gap. So there could be a 2 to the squared of n time algorithm, and that won't contradict p not equal np, but it would contradict this. Okay? All right. So besides Seth, there's 3 more commonly used hypotheses. So here they are. Again, we have to fix the machine model. 3-sum is a very simple problem. You have n numbers. Let's say they're integers. They're given to you. And you want to know if 3 of them sum to 0. This problem can be solved in quadratic time very easily. Using hashing, it will be expected quadratic, but you can even do worst case. And you can do slightly better than quadratic. You can get n squared over log n squared, both when the numbers are integers and when they're real numbers, depending on which model of computation you pick. But for whatever reason, we can't do better than this. And there's this hypothesis that has been around for a long time that says that threesome actually requires quadratic time. You may be able to get polylog improvements, but you won't be able to get n to the 1.999. That's threesome. And this problem has been used for hardness results in computational geometry for many years. This is another problem called orthogonal vectors. Here you're given n very short binary vectors. And all you want to know is that are two of them orthogonal. Of course, you can go through all pairs of vectors, compute the inner product. Since they're very short, the inner product computation is very fast. And you can, of course, solve this problem in n squared times d time, where d is the dimension. And the best known algorithm is a little better. So if d is of the form c times log n, like 100 times log n, this will be better than quadratic. But the moment your dimension becomes super logarithmic, this is essentially n squared. So there's this hypothesis that says this problem requires quadratic time in the RAM model. Final problem from graph theory now. This one, you have an n-node graph. It has, let's say, non-negative integer weights. And you want to find the distance between every pair of nodes. You have all seen algorithms for this, like Floyd, Warsaw, and so on. They run in cubic time. The best algorithm is n cubed over an exponential of square root log n. But this exponential of square root of log n is smaller than any polynomial. So this will be worse than n to the 2.999, no matter how many nines you put in there. So a hypothesis from graph theory says, graph algorithm says, that this problem requires cubic time in the number of vertices. These are these three problems. Actually, there's really two, because Williams showed that the strong exponential time hypothesis implies this one. So if you believe that SAT requires 2 to the n time, then this orthogonal vectors problem also requires quadratic time. And I will show you how to prove this at the end of this tutorial. Okay? So really, it's threesome, all pair shortest path, and the strong exponential time hypothesis. Why do we have three and not just one? You know, in P versus NP is really just one problem, you know, that's everything is equivalent to. But actually, there's some sort of result that claims that if you believe some strengthening of the strong exponential time hypothesis, then these are not all equivalent to each other. So these could actually be completely different. But once you pick these three problems, you can show hardness for like a lot of stuff, a lot. And if you add more problems, you can also show even more. We'll just focus on these.
What's the sense in which the problems are non-equivalent? Like, what's the...
Is this non-deterministic strong ETH hypothesis?
If you assume that...
If you assume that, then you cannot reduce orthogonal vectors. There's no reduction, so there can't be. But it's a little shaky. It's just, okay, some reason. All right. Okay, so we're back here. So we have picked some hypotheses about 3 or 4 problems with corresponding running times. And now we have to talk about what the reductions look like. So before, we had these polynomial time reductions, and now we have to make them better so that we care about running times. So let's first recap what are these polynomial time reductions, if you have forgotten. So let's do it. Usually in NP hardness proofs, you talk about many one reductions. What is a many one reduction? From problem A to problem B, it's just a polynomial time algorithm. What does the polynomial time algorithm do? It takes an instance of problem A, runs this algorithm, gets a single instance of problem B. Because the running time is polynomial time, the size of the new instance is also polynomial. And then these are 2 decision problems, so both their answers are 0 or 1, no and yes. So once you get an instance of problem B, then you get, and if you solve it, you can solve A by just answering the same answer. So yes goes to yes, and no goes to no. These are many one reductions. And you can read the definition here. They have a lot of useful properties, but they have some issues when we talk about the problems we care about. So if you remember in the longest common subsequence problem, this was a function problem. It was not yes or no. We were asking what is the length of the longest common subsequence between these two sequences. You have to output a number, not 0, 1. So in these reduction over here, because you take a single instance and you produce a single instance, you really can only, the reduction can, any answer to B can only give you one bit of A, really. And so because of this, it's not, you can't reduce like a function problem to a decision problem using a menu one reduction. Instead of a menu one reduction, you can use something called a Turing reduction, where instead of producing a single instance, you produce many instances, and the answer of A, it depends on the answers of all of the ones you create here. But then there's this other issue, is that this sort of reduction only is required to take polynomial time. So it's too coarse-grained. It doesn't actually care about how long it takes for you to solve problem B. So having like a linear time algorithm for B will not let you solve A in linear time, because the blow-up of the reduction could be any polynomial. It could be n to the 100. So it's not useful for concrete running times. Okay, so this is it. So we need to fix it. How do we fix it? All right, so let's say A and B are two problems, and we care about the following running times. Running time A of n for problem A, and running time B of n for problem B. And we want our reduction to have the property that if you reduce A to B, then beating the naive running time B of n for B implies that you can also beat the A of n running time for A. All right, so let's do this. Okay, so let A and B be problems, A and B, little a and little b be some runtime functions. We say that A is AB reducible to B if the following lots of words hold. Let's look at the picture. What's the picture? The picture is as follows, okay? For every epsilon, there's some delta. Okay, so that means, what is the delta? You take any instance of problem A of length n, and there's some algorithm that is faster than A of n. So its running time is A of n to the 1 minus delta. And what does this algorithm do? It produces many instances, maybe one, but possibly many instances of problem B. And it produces them adaptively, so that maybe the instance over here could depend on the answers to the instances over here. This is what's called like making oracle calls. Anyway, so it produces many instances, and once you have the answers to all these instances, you get the answer of A to A, again in A of n to the 1 minus delta time. The sizes of these instances could be different. This one has size n1, n sub 2, n sub 3, and so on. But this red inequality holds. What does this red inequality say? Well, it basically says that if you can solve problem B in B of n to the 1 minus epsilon time, then solving each of these little ones over here, their running time will be the sum over I, the sum over all the instances, of the running time of this algorithm on each of these instances, which is B of n sub I to the 1 minus epsilon. And this inequality says when you sum the running times on each of these instances, you get something less than A of n to the 1 minus delta. Now together, basically all these instances can be solved in A of n to the 1 minus delta. Together with the reduction, which produces them and gets the answer to A, you get an A of n to the 1 minus delta time algorithm for A. Okay? So all the reduction has to do, it has to be an algorithm that given an instance of problem A produces many instances of problem B and uses them to solve problem A, and it has this inequality. Okay? Yeah?
How important will the adaptivity be? How important will the adaptivity be?
That's a good question. So many of the reductions that we have don't need it, but we will see one in the next lecture that actually does need adaptivity. It's actually very important when you try to reduce certain function problems to decision problems. But often you don't. Often, actually, you won't need to create many instances adaptively. But sometimes it's very useful. Okay, proposition 2. This is easy to prove. So it says if I can reduce A to B, AB reducible to B, and B is BC reducible to C, then A is AC reducible to C. That means if you can beat B of n for B, and then beat A of n for A, and then you can also beat C of n for C and use it to beat B of n for B, you can compose these reductions and get the following. And so just very similar to NP hardness reduction, you get these reductions composed. So you can use one reduction as a procedure inside another one and get these results. Questions about this definition?
The way you set it up is to enable compensation, probably, right?
Yes.
So you're saying that the reduction actually runs in more time than all my little minions kind of solving the problem.
Yeah, it can. And this is so that this is very powerful because now I can reduce a problem whose natural running time is, let's say, 2 to the n to one whose running time is n squared, or vice versa. You can do very interesting things with this. You can show things that are equivalent, so A, B equivalent. So if and only if, with different running times. All right. So we're here. Now we know what an HQ fine-grained reduction is. H and Q become, they were A and B, now they're H and Q. H for hard, Q is for questionable, okay? And now this is our approach. You assume this a hypothesis, give a reduction to problem Q, and then conclude that Q requires Q of n time now instead of H of n. Okay. Let's talk about NP hardness again. In 1972, CARP gave a list of 21 problems that are NP complete. In other words, they're all equivalent to each other and every problem in NP under polynomial time reductions. And this list has grown there's thousands and thousands NP complete problems nowadays. And there's also problems outside of NP that are NP hard. There's many of them. I just wrote one. So NP versus NP has been very influential in showing how hard certain problems can be. So what do we know? Well, not as much. But here's some things we know, and I didn't have space to put everything that we know. So if you remember, we have these 3 problems together with SAT, and these orange things say like 3-sum is, we assume you cannot solve 3-sum in less than quadratic time, n to the 2 minus epsilon. You assume that all pair shortest paths cannot be solved faster than n to the 3 minus n cubed times, so you can't get an n to the 2.9. And orthogonal vectors can't be solved faster than n squared. K-sat can't be solved faster than 2 to the n, that's strong ETH. And assuming these, now you can get these reductions to a lot of problems. From all pair shortest paths, you can get equivalences. And they're all of the form n cubed equivalences. So if for many graph problems, if you can solve them faster than cubic time, you can solve all pair shortest paths faster than cubic time, and vice versa. And I will show you some of these reductions in the next lecture. From orthogonal vectors, we have very few equivalences. I haven't shown them here. But once you assume that strong ETH holds, or that orthogonal vectors requires quadratic time, you get a lot of things. In particular, you get the longest common subsequence requires quadratic time. So if you assume SAT requires 2 to the n time, then longest common subsequence requires n squared, and many other problems like graph diameter. There's some problems in machine learning also that were shown to be hard. From 3-sum, you can give there's been a lot of work in geometry showing that a lot of geometric problems require quadratic time and beyond, assuming threesome requires quadratic time. And recent work has shown things about sequence alignment problems similar to longest common subsequence, but slightly different, again from threesome. And this list keeps growing and growing, and some problems are actually hard from all three hypotheses, and so on. Okay, so this is the picture. What I'm going to show and what I'm going to do in the next few minutes, I'm going to actually give you this reduction. I'm going to show you how you can take the satisfiability problem and give a fine-grained reduction to orthogonal vectors. Okay? So you can see how a problem in 2 to the n time can be reduced to a problem in quadratic time. Questions before this? Okay. All right, so we'll do our first hardness example. All right, let me remind you what orthogonal vectors is. You have n binary vectors, so 0, 1, of very small dimension, n to the little of 1. Think of the dimension as log n squared, a very small thing. And the set of vectors is S1 to Sn. Are there two of these vectors that are orthogonal? That's what we want to know. Equivalently, because the vectors are binary, I want to know if there's two vectors such that in every coordinate, either the first one or the second one is 0. Okay, that's all we need to know. All right, easy to solve in quadratic time, and the best known algorithm is basically quadratic. We're going to prove this theorem, which was proven by Ryan Williams in 2004, that if orthogonal vectors has a subquadratic time algorithm, so for any epsilon, then the strong exponential time hypothesis for SAT is false. I'm going to remind you what Seth is, okay? It says that for every epsilon, there's some k, there's some clause with k, so the k sat on n variables and m clauses can't be solved in 2 to the 1 minus epsilon to the n times poly m time. So in other words, if you get an algorithm for SAT for with such a running time, and that algorithm can solve SAT for any CNF formula, for any clause with k, this is what will refute the strong exponential time hypothesis. And the theorem says that if OV, orthogonal vectors, has a subquadratic time algorithm, then such an algorithm must exist for SAT as well, but now beating 2 to the n instead of n squared. So now we will try to prove this theorem by getting a reduction, a fine-grained reduction, 2 to the n, comma n squared, fine-grained reduction from SAT to orthogonal vectors.
So SAT could potentially be easier, right?
Absolutely. In fact, I believe it is easier, but yeah.
And there's no hope to kind of like even
Reduce the other way.
the other way because you have to compress instances.
I've tried, yeah. I don't know how to compress. So he's saying, can't we just show maybe that orthogonal vectors can also be reduced to SAT? But there's some certain difficulties there because now you have a problem in quadratic time and you need to create a problem that requires exponential time, which kind of, if you were doing a many one reduction, you're creating a single instance, you have issues with that because now you have something of length n, and now you have to make it into something of length log n, basically, because n squared needs to become 2 to the n. So, but in order to do that, like you might want, maybe you can do a fine-grained reduction where you create many instances, and I've tried, but it's very hard. You have to parallelize the computation somehow, right? Mm-hmm.
Does this feel like controversial, like in the sense that like do people like outright reject these hypotheses?
I want to refute these hypotheses. In particular, the strong exponential time hypothesis. That would be the easiest to refute, perhaps. You just get 1.9 to the n time algorithm, right? Except a lot of people have tried for many, and they still try. There's these SAT competitions, SAT solving competitions. They try all sorts of algorithms, and yet that's where we are. In fact, it's even worse. There's a super strong exponential time hypothesis which not only does it say you can't, so yeah, it says, can you beat this? This K dependence over here for K-sat. Can you do better than that? And there's a super strong ETH which says you cannot. So just beat that, okay? Well, that would be great. Put like a inverse Ackermann over here, you know? That would be just wonderful. Anyway, so yeah, it would be great to refute these, any one of them. This one, or like all pair shortest path, solve it, and enter the 2.999 time. Yeah, that would be great, but we're stuck on that. Yeah. Anyway, so right now we're just, oh, by the way, you can just think of these reductions as attempts to refute these hypotheses. Because, you know, maybe it's so hard to get it better than 2 to the n time algorithm. Maybe like if you look at these polynomial time problems, we're really good at reasoning about polynomial time problems, right? We throw a bunch of techniques and maybe we can get a better than n squared time algorithms for orthogonal vectors. Yeah, why not? So these reductions kind of pinpoint to what you should focus on. All right. Here's the reduction. So let's say we're given a formula, a SAT formula, on n variables and m clauses, and like, for example, this one, okay? Let's say we have an algorithm for orthogonal vectors. Again, orthogonal vectors is you have n vectors that are binary, small dimension, are there two that are orthogonal. Now, our algorithm for OV supposedly is very fast, so we want to use it to solve SAT. So in order to do that, we have to convert this formula into some instance or instances of orthogonal vectors. Okay? So let's say we want to, from a single formula, create a single instance of OV. So that means, given f, we want to create a set of vectors that are binary and small dimension, so that there is an orthogonal pair if and only if f is satisfiable. And the number of vectors, let's say, is 2 to the n over 2, because supposedly this algorithm is subquadratic, and if we run it on something that's roughly 2 to the n over 2, this when you square it, you'll get something better than 2 to the n. And you want the dimension to be small. Let's say the dimension is the number of clauses. That's what we're going to try to do. Okay, so how are we going to do this? So take the set of variables of the formula, V, and split them. Remember, there's n of them. Split them into two halves. Each V1 has the first n over 2 variables, and V2 has the second n over 2. So like, for example, for this formula, there's 4 variables. We put the first 2 in V1, the second 2 in V2. Then, now that we have V1 and V2 of size n over 2 each, what is 2 to the n over 2? Well, we can look at all possible partial assignments to the variables in V1 and all possible partial Boolean assignments to the variables in V2, right? So, for example, for V1, which is x1 and x2 here, the set of 2 to the n over 2 assignments to V1 are just x1 and x2 are both 0, x1 is 0, x2 is 1, x1 is 1, and x2 is 0, and both of them are 1. So there's 2 to the n over 2 of them for V1 and 2 to the n over 2 of them for V2. Okay? So now the idea is, for each of these 2 to the n over 2 Boolean assignments, we're going to create a vector. Okay? And then we're going to try to do it in such a way that if there's 2 vectors that are orthogonal, then the SAT formula is satisfiable, and otherwise, you know, no. All right, so that's what I just said on the previous slide. Take V1 or V2 and take every partial assignments to the variables, and for each partial assignment, create an m is the number of clauses, okay, m plus 2 length vector, which I'll denote as Vj phi. J is 1 or 2, phi is a a partial assignment to the variables of Vj. What do? Let's say for V1, I'm going to put 0, 1 for every V1 comma phi for the first two coordinates. And then for the last m coordinates, every coordinate will correspond to a clause in the variable. And I will look at the assignment to the variables of V1, and I'll either put a 0 or a 1 in that coordinate. I'll put a 0 if that partial assignment satisfies the clause, and I'll put a 1 if it does not satisfy the clause. Okay? The same for V2, except now instead of 0, 1 over here, I put 1, 0. So 0, 1, it means that we're talking about partial assignments to V1. 1, 0 means we're talking about partial assignments to V2. And again, if the partial assignment satisfies the clause, you put a 0 and 1 if it doesn't. I'll give an example, okay? Here is my formula, this 3 clauses and 4 variables. V1 is x1, x2. And let's say I look at the assignment, x1 is 0 and x2 is 0. This is the vector I'll create. It will have 0, 1 in the first two positions because we're talking about V1, and for V1, every vector started with 0, 1. Then, for this assignment, I look at the first clause. The first clause is not satisfied by this assignment because both x1 and x2 are set to 0, so I put a 1 in this position. The second clause is satisfied because x1 is set to 0, so this not x1 is 1. So this is satisfied, so I put a 0 in this position. And the last clause over here doesn't contain x1 or x2, so there's no way any assignment to them could satisfy it. So I put a 1. Okay? This is how it goes. Any questions about this reduction? I will show you why it works on the next slide. Okay? But it's clear, right, that the number of vectors I create is 2 times 2 to the n over 2, because there's V1 and V2, there's 2 of them, and for each of them, there's 2 to the n over 2 partial assignments here. So there's 2 times 2 to the n over 2 such vectors, right? And it's very easy to create these vectors. Their length is m plus 2, m is the number of clauses, and you can just create them by checking whether the partial assignment satisfies the clauses or not. Super fast. Yes, so this is the example over here. So this clause, x1 and x2 do not appear in it. So then there's no assignment to x1 and x2 could satisfy it. So then I just put a 1 because it does not satisfy it. Trivially, it doesn't. Okay? All right. So I only put a 0 if there's some variable that does appear in the clause, and it also is set to the value that satisfies the clause. Okay. Here it is again. Now we're going to prove that it works. Okay, first, let's look over here. Why do we put 0, 1 over here? That is, if I take phi and phi prime that are different partial assignments to V1, their vectors cannot be orthogonal. Because of the first two coordinates, they will both have a 1 in this coordinate, so their inner product is non-zero. The same with V2. 2 partial assignments to V2 will agree on this coordinate over here, so they cannot be orthogonal. The only way for 2 vectors to be orthogonal is if one is for V1 and the other one is for V2. Okay? What happens then? Well, the claim is that if I have a phi, which is a partial assignment to V1, and psi, which is a partial assignment to V2, they're orthogonal if and only if, when you concatenate those assignments, you get a full satisfying assignment to the formula. This is true because being orthogonal means that for every coordinate, at least one of them is 0. It's equivalent. Now, at least one of them is 0 by this construction means that at least one of the partial assignments satisfies the clause. So by construction, being orthogonal is equivalent to saying for every clause, at least one of the partial assignments satisfies it. So when you concatenate those 2 partial assignments, for every clause, it's satisfied. it's equivalent. So the only way you have to have two orthogonal vectors is if the formula is satisfiable. All right? In other words, the set of vectors, v1 phi for partial assignments to v1 and v2 psi for partial assignments to v2, has an orthogonal pair if and only if the set formula is satisfiable. The number of vectors is 2 times 2 to the n over 2. Their dimension is m, the number of clauses. And it's an orthogonal vectors instance. If you could solve orthogonal vectors in subquadratic time, maybe with some polynomial dependence on the dimension, then when you plug n equals 2 to the n over 2 and d equals n, you get a 2 to the n minus something, times a polynomial in m, time for sat. And the strong exponential time hypothesis must be false. Okay.
So two questions. So the first two coordinates are somehow special? The dimension of these vectors is exactly m?
It's m plus 2.
What's the point of the first two coordinates?
So that your orthogonal vectors instance has a single set. Its input is one set, right? This entire set of vectors. So it's not like two different sets. So now I give you this set, and the only possible pairs that are orthogonal is if one is to the first half of the variables and the other one is to the second half. Right.
The second question is like, can you potentially do like n squared times d is a trivial algorithm, right? So this doesn't rule out like an n squared times square root d algorithm, for example.
Okay, look over here. Now, this, the way I stated it, so he wants me to say more that I didn't want to say. All right, so so there's something called a sparsification lemma for SAT, which takes a formula on m clauses and makes m into basically n. All right, n is the number of variables. So even if you have a huge number of clauses, there's an algorithm that can produce instances of SAT whose number of clauses is linear in the number of variables. And then if you run this reduction on what you get from the sparsification lemma, what you're saying will actually also refute stronger TH. So this is like, I wanted to avoid this because it's extra technical things, but you don't actually need this poly D there necessarily. All right. Okay, so that's all I had for today. For this lecture, and the next lecture will give you more. All right, welcome back. So now we're going to apply what we learned from the previous lecture to a bunch of problems, and I will focus on certain graph problems, very simple, shortest path-like problems, and we'll build a web of reductions. Okay? Let's define our problems. We'll have undirected graphs. There's no directions. They'll have weights. Think of the weights as non-negative integers. Sometimes there'll be negative ones as well. There's n nodes, m edges. What are the parameters? OK, let's take any vertex x, and we can define the eccentricity of x. What's that? That's the maximum distance you can go out from x. So out of all the vertices y, the maximum distance from x to y. That's the eccentricity. It's an eccentric name. I don't know who came up with it. All right. What is the diameter? The diameter of a graph is the maximum out of all the eccentricities. It's also known as the maximum distance in the graph. The radius is the minimum eccentricity. You can think of finding a node x, which is called the center of a graph, so that you can reach every other node in the graph within the radius distance, the minimum distance that you can reach everybody else, so in the center. The median is a completely different notion, but it's again based on distances. So now instead of maximizing or minimizing, you're summing up all the distances. For each x, you sum all the distances for over all y, and then you minimize over all x. That's the median of the graph, and there's other notions of centrality in graphs as well. For all these problems, you can solve them by computing all pairwise distances in the graph, so all pair shortest paths, which, as we saw in the previous lecture, can be done in cubic time in the number of vertices. You can save a little bit over cubic. For dense graphs, for sparse graphs, you can do m times n times some polylogs. For example, if the weights are non-negative, you can run Dijkstra's algorithm from every node. You'll compute all the distances. So we'll look at two different regimes. One regime is where the number of edges is roughly n squared. And there, the all-pair shortest path problem seems to require cubic time. And when the other regime is the sparse regime, where the number of edges is roughly the number of vertices. And there, all-pair shortest path is in n squared time, which notably is the best you can do because there are n squared pairs of vertices, and you have to compute a distance for every pair. Then, however, for these parameters over here, for example, diameter and radius and median, you're not computing n squared things. You're computing a single number. So there's no obvious n squared lower bound on the running time. And the question is, for sparse graphs, can you beat this n squared running time that comes from computing all pairwise distances? Can you get n to the 1.9? And for dense graphs, can you beat n cubed? So for all pair shortest paths, we assumed in the all pair shortest path hypothesis you can't beat n cubed, but these are different problems. You don't have to compute all the distances, so perhaps you can do better. All right, so these are the questions we'll try to answer right now. So what I'm going to do is I'm going to split the talk in two halves. The first half we'll talk about equivalences and hardness for dense graphs, and then we'll look at sparse graphs and also give some hardness there. All right. What we're going to show in the dense graph regime is that all pair shortest paths, the problem of computing all pairwise distances in a given graph, is actually fine-grained equivalent to radius, median, and all these other problems under subcubic fine-grained reductions. I'm going to remind you what a subcubic fine-grained reduction is from the previous talk. You take an instance of problem A, you run a subcubic time algorithm here, you produce instances of problem B, so that when you sum up, so n sub I is the size of the instance I of problem B. And when you sum n sub I to the 3 minus epsilon, you get less than n to the 3 minus delta. Therefore, if you can beat n cubed for problem B, you run this algorithm on the instances you create here, and you beat n cubed for problem A. This was the reduction, the notion. And we will actually show that all pair shortest paths is, for example, equivalent to the radius problem in graphs, so that if you can solve all pair shortest paths in subcubic time, you can solve radius in subcubic time. If you can solve radius in subcubic time, you can also solve all pair shortest paths in subcubic time, which actually is a more counterintuitive direction. All right, so here's a recap of what the equivalence means. All right. Why is it counterintuitive? Now, all pair shortest paths, as I said, you're outputting n squared numbers. Radius, you're outputting a single number. And here I'm telling you that if you give me a subcubic time algorithm, n to the 2.9 algorithm that computes a single number, I can use that algorithm to compute n squared numbers in subcubic time. Okay, so that's weird. And we'll see how to do that. Here is the research on all pair shortest paths. You may or may not have seen this, but in undergrad courses, we teach Floyd Warshall and sometimes Johnson and some other algorithms. But actually, there's been a lot of work in improving over n cubed. So in 1976, Fredman showed you can actually shave like log n to the 1/3 over n cubed. And this was later improved until the current best running time is n cubed to the square root of log n, okay, which is bad. I mean, it's much better than all of these, but it's still not n to the 2.9. And this is actually why we assume that we don't have a much better algorithm than n cubed for all pair shortest paths, because people tried, and yeah, for a long time it was actually stuck at n log squared over here. So, and for all the problems in the previous talk, I can flash you a similar slide where people try to shave something over the best running time, and and that was the best. And okay, so the APSP hypothesis was that in the RAM model of computation, you cannot do better, substantially better than n cubed. You may be able to shave some polylogs or slightly more than polylog, but you won't get into the 2.999. Now, if you can do better, that would be amazing. Actually, you should do that, please. But for now, we'll assume that we can't. Okay, so this is what we want to do. We want to show that a bunch of these problems are actually equivalent to all pair shortest paths, even though a single number is being computed. So how are we going to do that? The first thing is we're going to show that a lot of these problems here can be reduced to all pair shortest paths. And this is actually the easy direction. It's very easy. For example, for radius, you can compute all the pairwise distances. For every node, find the maximum distance out of it, and take the minimum out of these. And of course, if this is subcubic, then so is this one. And all these other problems can also be solved with using an algorithm for all pair shortest paths with a tiny overhead on top of it. So these yellow arrow reductions are very simple. Then the main work comes into having these equivalence reductions here, which I will show you, between all pair shortest paths and something called the distance product of matrices. And then between the distance product of matrices and a very simple problem called negative triangle. Then once we have those, we're going to have reductions from negative triangle to everything else, which is super simple. And now we have these cycles. Cycles, remember the fine-grained reductions compose. So a cycle means that these are just equivalent. Okay? Yeah.
Quick question. So this notion of equivalence and the notion of reduction is in some sense specific to the n-cubed location where you're reasoning about it. So suppose one of them had a complexity of n to the 2.1. It's not that this would be then equivalent to the other problem of n to the 2.1.
So in this case, these are all n cubed comma n cubed reductions. Now, there are examples in which you have an AB reduction from A to B and a BA reduction from B to A. And then you have AB equivalences. You can actually show this for different A's and B's and different A's and B's functions, which is weird, but I'm not going to show you that example there. We'll just focus on n cubed comma n cubed here. Mm-hmm. There was another question. Yeah.
Wait, so what's the runtime overhead of going from like radius to NPSP?
We will see. It's going to be very interesting. It will be like, as I defined in the previous lecture, all of these arrows are n cubed comma n cubed reductions. So an arrow from here to here means if I can solve APSP in n to the 2.9 time, let's say, then this problem can be solved in n to the 2.99 time. So as long as it preserves subcubicity. Okay. So it could be different subcubic algorithms, but still subcubic. Okay? And this will become clear in a little bit. So what I'm going to do first is I'm going to show you how these two are equivalent. I will define distance product, and I'll show that it's equivalent to all pair shortest paths. You may have seen this before, so it will go a little faster than usual. Bless you. All right. What is the distance product of matrices? A and B are two n by n matrices with, let's say, integer entries, and let's say I even allow infinity entries, whatever, or you can replace them with large enough integers. So you have integer matrices, and their distance product in the ij entry is the minimum over all k of aik plus bkj. Okay. The normal matrix product will have a sum and a times here. I replace the sum with a min and the times with a plus. It's also called the min plus product, or the matrix product over the tropical semi-ring, whatever you want to call it. It has many names, but this is the distance product. Okay, suppose I can solve all pairs shortest paths in t of n time, then I can also solve distance product of t of n time, because there's a direct correspondence between matrices and graphs. All right? So if I have a matrix, n by n, I can represent it as a bipartite graph, n nodes here and n nodes here. a node for every row of A and a node for every column of B. And I put an edge with a weight. So from 1 to 2 over here, I put an edge of weight 2. And from 2 to 1 over here, I put an edge of weight 5, and so on. If there happen to be infinity entries, you can just not put an edge. So I can put all the weights of the entries of the matrix A and encode them as this bipartite graph here. The matrix B, I can encode them as a bipartite graph over here, and they share the middle layer, which corresponds to the columns of A and the rows of B. And now, if I want the min, for every I and j, I want the min over I of aik plus bkj is the minimum weight of a path of length 2 from I to j. Because that's, yeah, you see? Which is exactly the distance in this graph, because there's no other paths from I to j, from I on the left and j to the right. So the min plus product, or distance product, can be translated into all pair shortest path problem, like this. And so if you can solve all pair shortest paths in t of n time, you can also solve distance product in t of 3n time or whatever. There's some constant in there, but it doesn't matter because these running times are polynomial. Okay? Questions about? Oh, yeah, wonderful question. Yeah, he says, well, the graph here is directed. But it turns out that because these are paths of length 2, I can increase the weights here and the weights here by a huge number. Just add the same huge number in here and the same huge number in here and remove the directions. It's because, like, in undirected graphs, in order to, to get a path of length more than 2, you have to go back and forth. And if you add something really big, you would increase the weight by too much. You're welcome. So you can also remove the directions, but this is pretty simple. Okay? Good. So this is very easy. So let's see the other direction. The other direction is if you can solve distance product in t of n time, then all pair shortest paths is in t of n times log n time. I removed the big O's because too much to write. All right. So let's take a graph in which I want to solve all pair shortest paths. Remember, it has, let's say it has non-negative integer weights. I can create an adjacency matrix of this graph, which is so it has n nodes, so then it's an n by n matrix. In the uv entry, we're going to put the weight of the edge uv, if uv is an edge, infinity if there's no edge between u and v, and 0 if u equals v. All right? So now what happens is, let's say I decide to do this distance product of a times a. Remember that the distance product is just the minimum weight of paths of length 2. For every pair of nodes, you take the minimum weight of a path of length 2. Okay? And actually, if you take the kth power of a under this distance product, you will get in the uv entry the minimum weight path of on at most k edges. At most k is because I put you can stay at the particular node with a cost of 0. Okay? So this means that, all right, so now shortest path. What about shortest path? How many possible edges can a shortest path have? Well, it turns out that without loss of generality, every shortest path is simple when the weights are non-negative. If you take, if actually simple means it doesn't repeat vertices. If you take a path that actually repeats vertices, that means it has a cycle on it. Now, if the weights are non-negative, that means that this cycle has weight at least 0. So I can remove this cycle, and now the path has one less cycle and has weight at most the original weight. So therefore, without loss of generality, all shortest paths between a pair of vertices have at most n minus 1 edges. Okay? So this means what I actually want to compute is the n minus first power under the distance product. So I have to multiply a by itself n minus 1 times. Or I could just do successive squaring. I take a, multiply by itself, I get a squared. Multiply a squared by a squared. And because this sort of product is associative, actually, I can do successive squared. And instead of doing multiplication n times, I do a log n times. And this is why we get T of n times log n. Okay? But I promised you an exact equivalence. Actually, it's also true that you can get rid of the log with a lot more work. This was proven by Fisher and Meyer in 1971. And it says that if distance product is in T of n time, if and only if all pair shortest path is in order T of order n time. Okay, so they're basically the same problem, if you think about it. All right? Good. So they're equivalent. And I didn't even need fine-grained reductions. They're exactly equivalent. So these are actually exactly equivalent. Now what I need to show you is actually this distance product is equivalent to something much simpler. Questions at this point? All right. We showed this in 2010. So what is this simple problem? It's called the negative triangle problem. You're given a graph on n vertices, and you have you have arbitrary integer weights on the edges. They could be negative or positive. And I want to know, is there a triangle in the graph, so 3 nodes, so that all pairs of edges between them exist, so that the sum of the edge weights is less than 0. For example, -3 minus 8 plus 10 is -1, which is less than 0, so this is a negative triangle. All right, but, and so the question is there a negative triangle? I can trivially solve it by enumerating over all triples of vertices in n cubed time, n is the number of vertices. Doing better would solve all pair shortest paths. That doesn't make any sense to me. When I first heard it, I was like, what are you talking about? But it's actually true. Yeah? You don't, yeah? Actually, it doesn't matter. Yeah, I drew it directed because it's nice to write it like this, but it actually doesn't have to be undirected. It can be made undirected. One way to think about it is, let's say I have a directed graph and I can triple the vertex set and just put undirected edges in the correct direction. From the first partition to the second, if the edges were from 1 to 2, and anyway. You can reduce the directed version to the undirected version. Okay, good question. All right. So in general, this is a very simple looking problem, and we don't know how to do better than cubic. And what we'll show is that it's actually equivalent to distance product. And here we're going to use the full power of fine-grained reductions. We're not going to create a single instance because all pair shortest paths is about n squared numbers, whereas negative triangle is a decision problem with only 1 bit answer. So you can't possibly reduce all pair shortest paths, a graph problem, to this decision problem in one go. You have to make many calls, maybe n squared. All right, so the reduction is going to go like this. We're going to take distance product, and first we're going to reduce it to an intermediate problem, which is this all pairs negative triangle problem. Instead of asking, is there a negative triangle, I will ask you, for every pairs of nodes, I to j, or ji, are there in a negative triangle? Which is equivalent to saying, for every I and j, is there some k, so the weight from I to k plus the weight from k to j is less than negative of the weight of ji, which is the same as the sum of these is less than 0. Okay, so all pairs, the only difference between negative triangle and all pairs negative triangle is here I need to know for every pair, is it in a negative triangle, whereas for negative triangle, I only need to know, is there any one of them. The second step will take all pairs negative triangles and reduce it to detecting a single negative triangle. And both of these will be n cubed, n cubed reductions. Okay? If it can solve negative triangle in subcubic time, it can solve all pairs negative triangle in subcubic time, and then you can solve distance product. All right. Questions about the way we're going to go? So he's asking, are the reductions dependent on the computational model? Not too dependent. We'll assume some random access sort of thing, but I think you can replace it with something else in other models. Yeah, you'll see, okay? Okay, I'm going to talk about the first step, which is you take the distance product problem, which is given matrices A and B, where you want to compute for every ij the min over k of aik plus bkj, that's distance product, and we want to reduce it to an all pairs negative triangle problem. To do this, first we take distance product and we represent it as a min weight two-path problem, as we did before. So now we take a tripartite graph. From partition I to partition K, we encode the matrix A. So in the IK, you put an edge from I to K with the weight AIK, and from K to J, you put the weight BKJ. And as we said before, the distance product is exactly to compute for every I and every J and J, the min weight path of length 2 between them. Okay, so for every I and J, the min weight 2 path between them. Now, imagine I added edges from J to I with some weights. How I pick the weights? Imagine someone gave me the weights. So I put some weights over here. And now I call all pairs negative triangle on this new graph. What does that give us? Well, all pairs negative triangles ask for every J and I, is there some K so that the AIK plus BKJ plus the weight that we added here gives us a negative number, which is the same as, is there K such that AIK plus BKJ is less than minus WJI, which is the same as, is the minimum overall K of AIK plus BKJ. Listen to this. Okay, I'll go back so you can see it. Is there some K that's less than this? Well, if there is some K, then the minimum one, the one that minimizes the sum, will also be less than this. So that's equivalent as the min over K of AIK plus BKJ. Listen to that. But this is the distance product entry of IJ. So if I put some weight over here, all pairs negative triangle can tell me for every J and I is the distance product entry of between I and J less than the weight that I put there. Okay, so this gives us a way to binary search for the distance. And this all pairs negative triangles answers all the queries for all n squared entries at once. So I can do a simultaneous binary search for all of them. I put some guess for every entry over here. It tells me a Boolean value for every ij, is it less than or greater than my guess? And then I have my guess when the entry is less, or put it in have the second interval otherwise. And I keep doing that. And now, as long as my weights over here are at most a polynomial, for example, like n to the 1000, the number of times I need to make these calls is logarithmic in n. And in general, if the weights are bounded by some m, it's log m. So with log m calls to this all pairs negative triangle problem, you can solve distance product. Okay? Now you may ask, oh, what about arbitrary integer weights? Actually, there is a way to deal with that too. So even if your weights are really huge, there is a different way, a randomized way to make this reduction work. But I'm not going to give this to you. So there's a different way where no matter what the weights are, you can make a logarithmic number of calls. Okay? So with this, we know that you can reduce distance product to all pairs negative triangles. Now we need to reduce this all pairs negative triangles problem to just detecting a single negative triangle. And this is the hard part of the reduction. Are there any questions about this so far? All right. Good. All right, let's do this. We're going to reduce all pairs negative triangles to just finding a single negative triangle. So the all pairs negative triangle problem, you have 3 parts, a tripartite graph, and for every red edge over here, every ij, I want to know if it's in some negative triangle. Okay? And the way I'm going to reduce this to checking for a single negative triangle will be to split every part over here. I'll split it into a bunch of pieces of small size, k into a number of pieces of small size, and j into a number of pieces of size. The size of the pieces is s, and the number of pieces is n over s. And then I'm going to look at all triples of pieces, I sub I, j sub j, and k sub k, and I'm going to try to find a negative triangle in there. And somehow, from the information from all these triples of pieces, I will be able to solve the all pairs negative triangle problem. Okay, so this is the beginning, and now we're going to see how to implement it. Okay, we have an all pairs negative triangle instance, and we have an algorithm that can detect whether any graph contains a negative triangle. Okay, and I'm actually going to assume that that algorithm can also find a negative triangle if one exists. This is actually without loss of generality. If you have a detection algorithm, you can also get a finding algorithm. I'll leave that as an exercise, but it's not hard. So here we're going to do, let's C will be our output. It's an n by n matrix. It starts with all zeros, and in the end, in the ij entry, it will say 0 if there's no negative triangle going through ij, and 1 if there is one. Okay, so it will be a Boolean matrix that will answer the all pairs negative triangle question. Now, I split I, j, and k into pieces of size s. And now for every triple of pieces, I1, J1, K1, for example, in the beginning, I'm going to, what am I going to do? I'm going to check, I'm going to run the negative triangle algorithm. And it's going to say, does this piece contain a negative triangle? The reason why I can do that is because these pieces are small. Each piece has size s, which is much smaller than n. So running negative triangle will be subcubic in s and not n. It will be super fast. Now I will know whether this piece over here contains a negative triangle. And as I said, I'll assume that I actually found the negative triangle. There it is, A3, A4, and A5. I find a negative triangle, and this negative triangle tells me that A3 and A5 are in a negative triangle. So I can just set the corresponding entry of C to 1, because I found that this entry should be 1, because it is in a negative triangle. All right, now what do I do next? I set the weight of this edge to infinity. Okay, fine. And then after I go through all possible, so whenever a triple no longer has a negative triangle, I move on to the next triple until I go through all possible triples, and then I return C. Okay, so this is basically like going through all possible negative triangles, essentially, except for this part over here where it sets some weight to infinity. Setting the weight to infinity ensures that this edge doesn't appear in any more negative triangles. Okay, this weight is so big it can no longer appear in negative triangles. But that is okay because I already determined it's in a negative triangle, and I don't need to look at it again. It doesn't affect the answers to any of the other queries. All right, so this is the entire reduction. If for every edge that does appear in a negative triangle, it will be found, because you go through all possible triples and you keep asking whether there's a negative triangle. And if you didn't find this edge, eventually it will be returned. Okay? So the only question is, so the correctness should be somewhat clear. So the only question is the running time of the reduction. Are there questions about the correctness? All right, well, I'll tell you about the correctness again. So I need to know for every pair, is it in some negative triangle? the third node of the negative triangle, if it exists, it appears in some triple, right? And when we run the negative triangle detection algorithm for that triple, this triangle is a potential thing that will be returned. And you keep running the algorithm until this triple of nodes no longer has a negative triangle algorithm. And when that happens, you have actually already found this triangle, or some other one including this edge. Okay? Yeah?
Did we choose the partitions I, J, and K in a particular way?
No, completely arbitrary. So I, J, and K actually are given to you because all pairs negative triangle is a problem on tripartite graphs. So they're given to you, but the way you partition them is completely arbitrary into pieces of size S. Yeah. All right. So here's your reduction, how it goes. What is the runtime? Now, every time you call negative triangle, you call it on a graph on 3 S nodes. So let's call it S. And the only thing we need to count is how many times you run this negative triangle algorithm. The number of times you run it depends on whether you found a negative triangle or whether you determine that there are no more negative triangles in the triple. The number of times you determine that there are no more negative triangles in IX, JY, and KZ is bounded by the number of triples, because you can only return no more negative triangles once per triple. Okay? So this is the number of times you run negative triangles when it said no more negative triangles. This is the number of times you found a negative triangle. The number of times you found a negative triangle is at most n squared, because the moment you find that this edge is in a negative triangle, you set its weight to infinity, effectively removing the edge. Okay? So the number of times you found a negative triangle is n squared. The number of times you determine that a triple no longer has one is n over s cubed. And as we often do in algorithms, in order to minimize this running time, you set n squared to n over s cubed. So when you set, so let's say the time to find a negative triangle is n to the d on graphs on n nodes. Then when you set s, the number of nodes in a part, to be n to the 1/3, and you plug in, you get a running time of n to the 2 plus d over 3. If d is less than 3, so the time to detect or find a negative triangle is subcubic, then so is this. Okay? So if you can detect a negative triangle, you can also determine for every edge is it in a negative triangle, and therefore solve distance product, and therefore solve all pairs shortest paths. Okay? So they're not exactly the same running time, but they're both subcubic. If one is subcubic, so is the other. All right? Questions? Yeah.
So, is this like a divide and conquer heuristic? Like, what would you call this? Like, when you make this split and you do the n over s thing? Is that like a well-known?
Sometimes it's called split and list. I don't know. Yeah. Split and list.
But you mentioned it's common to like set like that. Like the s equals n to the 1/3 is like a normal thing to do.
This, because, okay, so see, if s is bigger than n to the 1/3, then this will dominate. If it's less, then this will dominate. So to minimize the running time, you set them equal, and then you get that. All right.
Do you believe that they're of the same complexity, or?
Well, we've tried we've tried to improve this reduction. I don't know how to improve it. I mean, one thing is that this partition is completely arbitrary. What if we did something more fancy, like randomized? But it doesn't seem to give anything better. So they might actually be different. But if they're both, if you believe they can be in subcubic time, then they're the same. Yeah. All right. So what we've shown is that these are equivalent, and I will give you just one of these reductions because it's pretty simple. From negative triangle to radius. So if you could solve radius in undirected graphs in subcubic time, you can also solve negative triangle. Okay. Okay, so I'm going to modify negative triangle a little bit to make it nicer for us. So without loss of generality, the given graph is tripartite. If it's not, then you can make it tripartite by every node gets 3 copies and then add the edges, and every triangle is represented 6 times, and anyway, the usual thing. So without loss of generality, the negative triangle problem is in tripartite graphs. Moreover, without loss of generality, the graph is complete and undirected. The way you do that is by adding really huge weights. So if there was no edge, let's say the largest weight edge were m. If there was no edge, then we just add an edge of weight 3m. And this weight 3m, basically, even if your original weights were between minus m and m, adding 2 edges of weight minus m to 3m still gives you a positive number. So adding weight, basically 3m is basically infinity for this problem. So now we can just assume that the graph is complete, undirected, tripartite with weights between minus 3m and 3m. And in fact, I'm going to rename 3m by m. Okay? So now we have a complete tripartite graph with weights between minus m and m, and you want to know if there's a negative triangle. All right. I'm going to reduce this version of negative triangle to radius. If you recall what radius is to find the minimum over all the nodes u of the maximum of the distance from u to v over all v. So the minimum distance such that the center node can reach everybody else. What we're going to do first, we're going to take this tripartite graph, and in which you want to find a triangle of weight less than 0. And I pick some w, which is more than the maximum edge weight, and I add m plus w to every edge. And all this does is now the weights are between w and 2m plus w, and instead of finding a weight less than 0 triangle, you're finding a weight less than 3 times whatever you added triangle. So now you're looking for a triangle of weight less than 3m plus 3w. Okay? Just put huge weights, add huge weights to the edges. And now instead of less than 0, you're finding less than 3m plus 3w. Okay. Step 2, we're going to create a new graph out of this. Remember that the tripartite graph had partitions A, B, and C. We put a first copy of the nodes of A, a copy of the nodes of B, a copy of the nodes of C, and a second copy of the nodes of A. Between A and B, we put all the edges that were in the original tripartite graph between A and B with their weight here. Between B and C, we put all the edges as before. And between C and the second copy of A, we put the same edges as between C and A. So an original triangle between A, B, and C is now a path of length 4. Right? It's from the AB, BC, and CA. All right? So now instead of looking for a triangle of weight less than 3m plus 3w, I'm looking for a node A and its copy A prime so that there's a path of length less than 3m plus 3w between A and A prime. So I unfolded a tripartite graph. I took one of its partitions, split it into half, and now instead of having a triangle, I have a path on 4 nodes. Okay? Now, what I'm going to do is for every node A here and every node E on this side that is not A's copy, I'm just going to connect them with a direct edge with some weight that is less than 3m plus 3w. In fact, it's exactly 3m plus 2w. This will accomplish that instead of looking for A and its copy such that their weight is less than 3m plus 3w. I'm looking for some A such that the distance to every node over here is less than 3m plus 3w. Then I'm going to put some gadget over here. What does this gadget accomplish? It accomplishes, so I put these two nodes x and y here, and this accomplishes that for every node in A over here, I can reach every other node in here at a cost of 2m plus 2w, and I can reach z or w also at a cost less than 3m plus 3w. It also accomplishes the following thing. Every node, except for those nodes over here, are at a very large distance, less than at least 3m plus 3w, either from z to z or to w. So every node over here, recall that all these weights, we made them at least w. And so in order to go from this node over here all the way to z, you have to pay w plus m plus w plus 2m plus w, which is too much. And this is even further, and this is even further. So the only way to get close to z is if you're in here or in here. But then if you're this node, you're actually far from w. So basically, every node, except for these nodes, is too far from these two nodes. So that means that the center of the graph is actually in here by construction. The center of the graph is actually in here, and it's the radius is actually, if this is the center, the radius is actually determined by the distance from A to its copy, because A is close to every other node. In fact, we can see that the distance for every node in here to every node in here is at most 2m plus w, because the original graph was complete, and the weights are at most 2m plus w. The distance from A to here is at most twice this, which is still less than 3m plus 3w. And the distance from A to this node over here is, we put a direct edge, which was already too big. It was already small enough. So the only large weights, possible distances, are between A and its copy. So the radius is less than 3m plus 3w, if and only if there was a negative triangle. Okay, so this is much simpler than the previous reduction. You just have to deal with a bunch of weird weights and make everything just work out just right. But it's just a single instance that you create. And you convert a negative triangle to a center node, basically. Okay, any questions about this? Yeah.
Are there any known reductions from directly from radius to produce like a negative triangle? Because it seems really hard to make one if this was what was necessary to go from negative triangle to radius.
Yeah, to go from radius to negative triangle, the only reductions we know is to go to all pair shortest paths and then to the other way. Yeah, it's a good question. You can try to figure it out, but yeah, just several steps. Yeah. Okay, but this completes kind of the cycle. So radius is equivalent to all pair shortest paths and negative triangle. Yeah, you see here, we did this. We did these, we did this, and this. This is easy because you can solve radius with all pair shortest path. All right, so I'm not going to do any of the others, but they follow a similar sort of strategy. We already have this part, and then you have to mess with the weights and create special graphs in order for everything else to work out. All right. Now we're going to do a little bit on sparse graphs, and these will be much simpler, I promise. All right. All right. What is a sparse graph regime? So all these problems that I defined, diameter, radius, whatever, medium, they all can be solved in n² time just by running all pair shortest paths. And this is the best known. So the number of nodes is n, the number of edges is essentially n times polylog n. And as I mentioned, the output of all these problems over here for diameter, radius, median is a single integer, not like APSP, so it's unclear why you need to pay n² time. And what if I don't really care about exact solutions? What if I want to approximate these numbers? want to get approximate diameter, approximate radius, approximate median. What can I do? So here's some things that are known. So diameter, the best subquadratic time approximation algorithm is a 3/2 approximation, which returns a distance that's at least 2 times the diameter over 3 in time like m to the 3/2 or whatever. So if m is essentially n, it's n to the 1.5. For radius, is the same. You can actually do all the eccentricities also in n to the 1.5, but the approximation factor becomes 5 over 3. Median, you can do almost linear time in 1 plus epsilon approximation, so it's much easier. So the question is, why can't we make these like median and have them have a near linear time approximation algorithms? And we will see that under some interesting hypotheses, like the strong exponential time hypothesis, this won't be possible. In fact, we'll show that these approximation ratios, 3/2 and 3/2 and 5/3, are actually tight for subquadratic time algorithms. What are the hypotheses? It's orthogonal vectors. It appeared again from the previous lecture. Given two sets U and V of n vectors that are binary with a tiny dimension, are two of them orthogonal? We assume that this problem requires n squared time, and we showed in the previous lecture that under the strong exponential time hypothesis, this requires quadratic time. Here's a slightly different problem from this one. It's the Hiding set problem. You're given two sets, U and V, of n subsets each of some small universe, k is small, and I want to know, is there a set in U that hits all the sets in V? In other words, for every set in V, U and V share an element. Turns out that there's this Hiding set hypothesis that says that this Hiding set problem also requires quadratic time. All right. There's also this theorem that we showed that if you believe this Hiding set hypothesis, then you should also believe orthogonal vectors requires quadratic time. There's no reduction in the other way, so this could actually be false, but no one seems to be able to disprove it. So if you want to spend time disproving some hypothesis related to orthogonal vectors, you should disprove this one. So we have, n sets of small size over small universe, and you want to check if some set hits all of them, all of the others. All right, so here's a web of reductions. We know that Hiding set can be n squared reduced to orthogonal vectors. Hiding set can be reduced to median and to getting a better than 3/2 approximation for radius in sparse graphs. So if you can get a better than 3/2 approximation in subquadratic time for radius, you refute this thing. Maybe you can do it. Now, for orthogonal vectors, it turns out that improving on the 3/2 approximation for diameter in subquadratic time, that will refute OV. And also improving the 5/3 approximation for the eccentricities problem also will refute OV. And of course, we know that SAT reduces to orthogonal vectors. So this is what we have. So what I'm going to try to do very quickly is actually show you very simple reductions from orthogonal vectors to diameter and Hiding set to radius, and they're basically the same. So I'll show you in a second. Ready? I can do it. Diameter 2 versus 3 is the following problem. I give you a graph on n nodes and a small number of edges, almost linear in n, and I want to know, is the diameter 2 or is at least 3? Okay? If you can distinguish between 2 and 3, then we will show you, in subquadratic time, then we'll show you can refute orthogonal vectors. Okay? And if you have a better than 3/2 approximation for diameter, then you can, of course, distinguish between 2 and 3. Okay. So here I will reduce orthogonal vectors. I take orthogonal vectors and I create a node for every vector. And then I create another copy of these nodes. So for every vector has 2 nodes. And in the middle, I have nodes for every coordinate. I put these two nodes over here, x and y. There is some gadget, and they have an edge between them. And I connect x to everything on the left and y to everything on the right. So this accomplishes that every node over here, every pair of nodes on the left have a path of length 2. Every pair of nodes on the right have a path of length 2. And every node in here and a node in here have a path of length 3. I also put edges from x to the middle and y to the middle, and this accomplishes that every coordinate is a distance 2 from every single node. So every pair of coordinates are distant 2, and then, you can use x and y to get everywhere from these coordinates. Okay? Then I look at every vector and every coordinate. And I say, I put an edge there if the vector has a 1 in that coordinate. If the vector has a 0 in that coordinate, I do not put an edge. Okay? Over here, for every vector and every coordinate, I put an edge if the vector is 1, and otherwise I don't put an edge. Okay? Now, two vectors, u and v, two vector nodes, u and v, on different sides are a distance 2 if they share a coordinate in which they're both 1. And otherwise, they're distance 3. Okay? So this means that the diameter is 3 if there exists an orthogonal pair, and it is 2 otherwise. All right? So every pair of nodes, except for the one on the left and one on the right, are distance 2. And those that are one on the left and one on the right are distance 2 only if they're not orthogonal. All right? There you go. How many nodes do we have? If the graph has n nodes, order n nodes, like whatever, 3n or something, and the number of edges is order n because if you recall, the number of coordinates here is very small. It's polylog. So it's tilde O of n edges, n times polylog n. So if you can distinguish between diameter 2 and 3 in subquadratic time, then you would solve orthogonal vectors in subquadratic time, and therefore the strong exponential time hypothesis will be false. Simple reduction. Single instance. It's not like the dense case where we had to wave our hands and imagine weights and so on. All right? Split a list. Nothing like that. All right. So we did this. I would do this one, which would be basically the same as this one. All right. Hitting set. What was hitting set? You're given two sets, V and U, of n subsets each of some universe from 1 to k, where k is tiny. It's like log squared of n. I want to know, is there a set in V such that for every set in U, V intersects U? So is there a set in U that hits all the sets in V? And we assume that the hitting set problem requires quadratic time. Now we're going to create a radius instance, very similar to before. I'm going to create a node for every set in V. And I'll create a node for every set in U. And I'll create a node for every element. Remember, the sets are of the elements from 1 to k. I'll put the same nodes x, y down here as before. I will connect x to everything in V, y to everything in U. Now the orange nodes are distance 2, and the yellow nodes are distance 2. I'll connect x to everything in the middle. Actually, I don't need to connect y to everything in the middle now. Now we have that every orange node is a distance at most 2 from every non-yellow node. So like it's the orange nodes between each other, they can go with it through x, they can go through x to the middle, and they can go through x and y to the yellow ones, but that's a distance 3. And then we do very similar things to the previous reduction. I'm going to put an edge between a set V and a coordinate, element C, if the element is inside the set. Okay? So VC is an edge if C is inside V. DU is an edge if D is inside U. All right? Now, two sets, U and V, from different sides are distance 2 if there's an element that is in both of them. So they intersect, right? I also put some extra node over here and another extra node over here and 2 nodes over here. This is very similar to the previous reduction. This makes sure that every non-orange node is a distance 3 from either R or S. R and S are distance 3, and everything in here has to go take at least a path of length 3 to go over here, and also here. So everything else except for the orange nodes are a distance at least 3 to R and S. So this means that the center node must be orange if the radius is less than 3, and the radius is 2 if a hitting set exists. So that means, so the radius can only be 2 if there's some node V that's orange that can get to everything in here at distance 2, which is the same as saying that this set intersects every set in here. There's some element that appears in both of them. So that means that, again, the graph has n nodes and roughly n edges, and the radius 2, distinguishing between radius 2 and 3 in subquadratic time would solve hitting set in subquadratic time. All right, so we did this, we did this one, and we did this one, and this one is similar, and I'm not going to do it. And also this one is similar. So a few final words about this. If you look at radius and diameter themselves, every single algorithm for them, if you can solve radius, you can solve diameter. In fact, you can solve all the eccentricities. Even the approximation algorithms, they have the same approximation ratios and running times. But they're different, which is why it's very difficult to reduce between them. They have different quantifiers. One is max, the diameter one, and the radius one is min-max, and that makes it difficult to reduce between them, even though both of them seem hard. In dense graphs, we have this reduction that showed that radius is equivalent to all pairs shortest paths, but we don't know such a reduction for diameter. Diameter actually could be easier in dense graphs. We don't have an algorithm, but there's no equivalence. Some problems are equivalent to diameter in dense graphs, but they're not equivalent to all pairs shortest paths. So we don't know. So there's open questions. Can you give any hardness for diameter in dense graphs? We don't have any. Can we get more equivalences? Can we actually relate the sparse and dense cases to each other? So far, we have completely different reductions. For the sparse cases, orthogonal vectors stuff. For the dense cases, all pair shortest path stuff. But there's nothing in between. Can we get any approximation hardness for dense graphs? We only talk about exact solution, but the approximation results are only for sparse graphs, and so on. So that's all I had to say.